Taking care to accurately model table structures is important for several reasons. One reason is because we want to define table structures to a degree of specificity that ensures MySQL is going to behave as expected when working with desirable table data, and to complain or outright prevent undesirable data from being managed within the table. A second reason is developer clarity. It should be possible for a developer to review a table structure and know exactly what are considered allowable values for this table. Simply put, the greater care you take to define table columns in a manner which precisely indicates their purpose, the less of a possibility that a fellow developer will misconstrue the intent and create an application which results in unwanted values being entered into the database. Returning to the employees column found in the customers table, we originally defined it as an integer, which makes sense because we want an integer value to be stored in that column, rather than something like the word 10. But because MySQL's integer data type has an extremely large default range, which you can see on the slide, it's entirely possible that a rather unrealistic integer value could be inserted into this column. For instance, we know of no company on the planet which has 2 billion employees. Not only could an unrealistic, particularly large value be inserted into the column, but a negative value could be inserted into the column. Beyond these issues, it's possible that a null value could be inserted, which is a SQL convention used to indicate when a value is unknown. I'll talk a bit more about this often confusing convention in just a bit, but nonetheless, we realize that it's unlikely we would want, in many cases, an unknown value to be inserted into a null value. To eliminate the possibility of such unwanted values from being inserted into a column, you can constrain a column in two ways. First, you'll logically assign a data type. You've already been acquainted with 4 such data types, including the varchar, char, integer, and date types. However, there are quite a few more data types supported by MySQL, which can serve to more accurately frame your intent. Beyond defining the data type, you'll supplement the column definition with attributes, which further tweak these constraints. Throughout the following sections, I'll talk at length about both MySQL supported data types and attributes. MySQL supports 8 different string types, each of which serves a specific purpose. So you've already learned about the char and varchar types, but to quickly recap, the char type is used when the string values are of a specific length, such as the 2-character abbreviations used to represent a U.S. state. These char types can contain up to 255 characters, so you're going to use char in conjunction with relatively short fixed-length strings. The varchar type is used for variable-length strings, consisting of up to 65,535 characters. So you would use the varchar type for things like people's names, email addresses, and street addresses. Or in other words, anything in which the length is unknown simply because of the variability that is inherent to those different types of data. The binary and var binary types are used for storing binary strings consisting of up to 255 and 65,535 bytes, respectively. Now notice I said bytes as opposed to characters, the latter of which is the unit of measurement for char and varchar. So binary and var binary are like char and varchar in the sense that they are used to store fixed and variable length strings. However, we are talking about binary strings, and the maximum lengths are represented in bytes. You would use these, of course, to store rather small bits of binary data. In my experience, frankly, binary and var binary data types aren't used particularly much. Rather, their much larger siblings are used quite a bit, which I'll talk about next. The blob and text types are used for storing very large amounts of string-based data. with the blob type intended to store very large binary string sequences, such as an image or a zip file. The text type is intended to store large non-binary strings, such as the text found in a book. Incidentally, there are a number of variations which allow you to constrain further the size of the blob and text types in different ways. There is a tiny blob, a tiny text, medium blob, medium text, and long blob and long text, in addition to the blob and text types, each of which has a different maximum allowable number of bytes or characters. You can read more about these different types within the MySQL documentation. The enum type, or enumerated type, identifies a list of permitted string values. So for instance, you might create a contacts table which associates individuals with a specific corporate customer and want to include a salutation column. So the salutation column might contain the following values: Mr., Mrs., Miss, Doctor, and Professor. And if those were the 5 values, and only the 5 values that you wanted to support, you could use an enum type to define those as the 5 allowable values. Once defined, MySQL will then consult this list each time a value in that column is created or modified to ensure that the value matches one of those found in the enum list. Believe it or not, the enum type can store up to 65,535 values. Finally, the set type operates in a manner similar to enum, in that you can store a list of acceptable string values, with the difference being it's possible to store multiple values rather than just one. So, for instance, you might use the set type to identify multiple preferred forms of communication, such as email, phone, and text message. Because a customer could conceivably prefer multiple forms, for instance, they might say it's okay to contact me via both email and phone, you would use this set type to identify those multiple accepted values. Although, as I mentioned, we would be revising the customers table throughout this section, let's take a moment to consider another table which takes into account some of the new data types introduced in this section. Our project's customers table, as we know, contains information about the various companies we do business with. However, ultimately, we will need to communicate with one or more specific contacts, so humans, associated with that customer. Therefore, we will want to additionally create a contacts table. So for the moment, let's disregard the fact you will need to relate the contacts and customers table and just focus on those fields associated with a typical contact profile, such as the contact's name, phone number, email address, salutation, and preferred contact method. So I'll go ahead and create the contacts table. Again, identifying a varchar with a maximum length of 255 for the name. We'll add a phone number, constraining the variable length on the varchar. We'll add an email address. Again, varchar, nothing new here. Email addresses can tend to be rather long, so let's not take our chances. Now we'll take into account an enum for our salutation, assigning it Mr., Mrs., Miss, Doctor, and finally Professor, and also a contact method. Remember, we acknowledge the fact that some contacts like to be contacted using a variety of methods. So we're going to use a set here. Email, phone, finally text message. Close the table definition, and we can run describe contacts to take a look at the table schema and make sure everything's okay. The not null attribute is not limited to solely string-based data types. In fact, you can use it in association with every other data type available to MySQL. Therefore, let's revise the customers table definition, this time using not null to supplement the columns. So we'll start out with create table, customers, identify the name column, which will be a var_char of a maximum length of 255 characters. We never want the null value to be allowed, so we'll set it to not null. Same goes for email, 255 characters, not null. Now, the employees column, which is used to determine or to set the number of employees associated with a customer, it's an interesting one because unlike name or email, it might not necessarily be a requirement that the person responsible for entering customer information into the database, it might not be necessarily that they know this employee count at this particular moment. So you could make a case for allowing a null value to be inserted into this column. Moving on, however, the state column, which is a char with a maximum allowable character count of 2, you certainly want this to be set to not null because it would seem to me a necessity that the state value is tracked at all times. And finally, we also wanted to know at all times that the date in which the customer became affiliated with our company. We always want to know that, so we're going to set this to not null as well. And if we run describe customers, you'll see that in fact name and email are not nullable, employees is nullable, state and customer since are not nullable. Now, interestingly, you might notice that although again, these columns are set to not null, these 4, at any rate, name, email, state, and customer since. You might notice that this default value is set to null, which really doesn't make a lot of sense. It's rather illogical. In fact, it's impossible, because if we're saying that these 4 columns can never be null, then why in the world is the default value set to null? Just some odd behavior on the part of MySQL. And in fact, it's not even a terribly big deal, in my opinion, because you would rarely allow such a default value to be set in this way, instead explicitly passing a value from your application, right? Nonetheless, you could in fact clear up this confusion within your schema, which I do recommend, and use the default attribute to set a default value. However, I'm getting a bit tired of typing, in particular typing the customer's creation statement over and over again, so I'm going to show you how to use the alter statement to alter an existing table. So just as a random example, we will assign the name column a default value of Jerry. So we'll say alter table customers change column name, and here you're going to repeat name var_char. We still want it to be set to 255 maximum characters, not null, and then finally default Jerry. I'll go ahead and run describe customers again, and you'll see that Jerry is now the default. Chances are your future databases will manage a wide variety of numeric data, such as geographical coordinates, salaries, and temperatures. Fortunately, MySQL supports a wide range of numeric data types capable of effectively managing integers, floating point numbers, and fixed point numbers. You've already been acquainted with the integer type because we used it in the customers table to store the employee count. However, using the integer type for this sort of data is likely overkill because it supports a range of integer values between roughly -2 billion and +2 billion. Because even the largest employer in the United States, which at this time happens to be Walmart, employs only around 1.2 million people, you could create a far more accurate representation of the employees column by using the medium int type, which has a range of between approximately -8 million and +8 million. Other types are supported for columns expected to fall within even smaller ranges. So for instance, small int supports up to roughly 32,000 on both the positive and negative side, and tiny int supports a range of between -128 and 127. Finally, if your range is expected to be unusually large, you might consider big int, which as you can see from the slide, sports a range larger than I care to decipher. Also at your disposal is the float, which is useful for storing what are known as single precision floating point numbers. The float is capable of storing a rather large range of values, which you can see the range on the slide. But it's very important that you understand float values are approximated, meaning that if your application requires absolute precision, you should instead use the decimal type, which I'll introduce in just a moment. However, the float type is likely perfectly suitable for storing information such as geographic coordinates, which for many cases tend to diminish in practicality at very high precisions. The float is generally accurate to 7 decimal places. So notice how this example defines a column used to store the latitudinal component of a set of geographical coordinates. In this example, we pass in 2 values to the float specification. The first number, 10, determines the total number of digits found in the number. The second number, 6, determines the total count of digits found to the right of the decimal point. If you are looking for a floating point type supporting a higher degree of precision, then check out the double type. It's also a floating point number that supports a very large range of numbers, as you can see here. However, whereas the float is accurate to approximately 7 decimal places, the double is accurate to approximately 15 decimal places. If you'd like to manage decimal numbers with exact specificity, such as product prices or salaries, then you're going to want to use the decimal type. You'll define decimal-based columns just like you would a float or a double, identifying the maximum number of digits and then the number of digits appearing after the decimal point. Therefore, given this price definition example, you could store prices ranging between -100 and 100. Now, we'll come back to this matter of supporting negative price numbers in a moment, or I should say, making sure that they can never occur. But for the moment, just keep in mind that you define decimal columns just as you would float or double columns, identifying both the total number of digits and then the number of digits following the decimal point. Finally, the Boolean data type is useful for storing truth values. MySQL happens to take a little shortcut in that its Boolean data type is supported by simply aliasing the Boolean keyword to tinyInt. And if you recall, tinyInt supports a range of integer values between -128 and 127. So what you would do is you would use the integer value 1 to represent true and 0 to represent false. You might use, for instance, the Boolean type to determine whether a new customer has been sent a gift basket, as demonstrated by this example. A customer's gift basket value of 1 would indicate that the customer has been sent the basket, whereas 0 would indicate that it had not been sent. When introducing the decimal type, I provided an example price column defined as decimal, capable of representing a value between -100 and 100. This actually doesn't make a lot of sense because prices are logically positive decimal numbers. You can prevent negative numbers from being stored in each of MySQL's supported numeric types by using the unsigned attribute. Therefore, the revised price example presented here will only allow values of between 0.00 and 100.00 because we've identified the column as unsigned. When used in conjunction with integer values, the unsigned attribute has a secondary effect in that it doubles effectively the positive side of the supported range. So, for instance, the second example uses a tinyInt, which is unsigned. tinyInt by default has a range of between -128 and 127, but when it's unsigned, it has a range of between 0 and 255. So, as I mentioned, effectively doubling it. You can also use the zerofill attribute, which will pad the displayed value with zeros up to the display width. So the invoice example presented here uses zerofill in conjunction with a display value passed into the integer type. definition to determine how many zeros should be placed in front of an integer number, which doesn't by itself consist of, in this case, 6 digits. Therefore, 1 becomes 0, 0, 0, 0, 0, 1, and so on. You can see 2 other examples here, including the last one, which notably is not padded with zeros because the number already consists of 6 digits. Now, I do want to point out that when you pass that display width, which in this case is 6, to an integer-based data type, it is only there to affect the display value. Integer has a range of between more or less negative 2 billion and 2 billion. Therefore, if you passed in 1 million into the column, it in fact will remain 1 million. Nothing funny is going to happen under the covers in terms of how MySQL treats that number. It's only when that number is displayed that that display number will affect MySQL's output. The final set of data types I'd like to introduce are those useful for managing temporal data, or dates and times. You might, for instance, want to record employee birth dates, the date a particular product was manufactured, or know exactly when a particular customer record was created or updated, a task known as timestamping. Well, it might be tempting to use MySQL's string-based data types, such as varchar or char, to manage this sort of information, because after all, dates and times can easily be saved and read as strings. In doing so, you'll miss out on a whole range of interesting MySQL features, such as the ability to compare dates and times, or add and subtract dates to and from one another, and format dates in a variety of flexible ways. So in order to take advantage of these capabilities, you'll need to use MySQL's date and time data types. Perhaps the easiest of these supported date and time data types to understand is the year type. The year type supports 2 formats really for storing years. The 4-digit format, so a year stored in 4-digit form such as 2011, supports a range of years between 1901 and 2155. It also supports a 2-digit format such as 11, which we would presumably take to mean 2011. However, this 2-digit format, in my opinion, is a tad strange, and I really don't recommend using it because of the rather limited range. As you can see here on the slide, the 2-digit format supports a range of 2000 to 2069 when the number is ranging between 00 and 69. And then 1970 to 1999, the 2-digit year provided, ranges between 70 and 99. As you can see, what the MySQL developers have done here is attempt to eliminate the possibility of ambiguity, because if I provide 11, who knows whether that's 2011 or 1911? They try and remove this ambiguity by just making the decision for you. Well, it takes a little bit of understanding of the MySQL internals, namely by reading the documentation, in order to understand this. So I certainly recommend using the 4-digit format when possible. So as you can see, the example here is a column called birth_year, and we would, if we're only interested in tracking the person's year rather than the entire birth date, we could use the year data type, and we also want to make sure that that is not set to null. The second date and time related data type that I'd like to show you is the date type, which you've already seen several times in the previous customers examples. The date type stores a complete date consisting of a year, month, and day, and the range here is between January 1st, year 1000, and December 31st, year 9999. So the example you see here shows an instance where we do want to store the person's entire birth date. We would use the date column and again make sure that it cannot be set to null. The third type is date time. So this date time goes beyond what date offers in that it stores both the date and the time, supporting the same date-related range, again, January 1st, 1000 to December 31st, 9999, but also, as you can see, stores all times found within that period as well. So the example here shows a column where we might be running a special for a particular product that we're selling, and it's going to expire at a very specific date and time. So October 31st, 2011 at 6 p.m. So we could use the date time to identify the very specific expiration date and time, and again, set it to not null. The final date and time data type that I'd like to introduce is the timestamp. The timestamp differs from year, date, and date time in that MySQL will automatically record, for most configurations, the current date and time for you. So you'll effectively timestamp a record or a new row when it's created by assigning whatever the column is, the timestamp column, assigning the current date and time. So this is useful for tracking when a record was created or when a record was updated. So in this example, and this is a very common example that you'll see in many tables, we have a created _on column. We've set it to timestamp and not null. So what will happen is when a new record is created for that table, that created _on column will automatically be assigned the current date and time. So you don't have to pass in a specific value, something that is required for year, date, and date time. The date, time, and timestamp columns are all pretty forgiving in terms of how values are passed to them. So as you can see, these three examples all demonstrate different formatting variations which can be used when passing in values to, for instance, date. So you can have dashes separating the year, the month, and the day, or slashes, or provided that the three pieces of data are all valid, you can eliminate the delimitation altogether. So that third one is 2011, 10/6. Now, if you tried to pass in 2011, 13/06, you'll receive an error, and MySQL will in fact not set that properly because 13, of course, is not a valid month index value. But I would like to return to the timestamp column because its behavior can at times be quite confusing to new users, and much of the confusion stems from the wide variety of configuration options at your disposal. So the example provided on the previous slide is a tad misleading in that I mentioned that the intent there is to timestamp the created _on column when the new record is created. So we're going to assign at the time that new customer has been added to our table, we want to know exactly when it was added. Well, the problem with the way it was defined on the previous slide is that the current timestamp will both be created when the row is created, but it will also be updated every time any other column in that row is updated, which of course is going to produce a lot of misleading created on timestamps. So you would use this particular definition when the goal is to both create a timestamp and then update it every single time another piece of information in that row is updated. If you do want a timestamp created when a row is created but never updated, you would define the column like this: created _on, timestamp, not null, and then default current _timestamp. Likewise, you might want to create a timestamp column which is not updated when a new row is created. That is, it's just set to some default 0 value, and then set to the current timestamp when the row is updated. You'll see a lot of tables that have a created on column and then an updated on column. So the created on column is only updated once, and that is when the new row is created. The updated on column is not updated to the current timestamp when the row is created. However, it is updated every time that row is updated. This example demonstrates how that's done. So what I'd like to do is show you how you can add both of these to a table, because this really does cause a lot of confusion among MySQL beginners. And the reason has to do with MySQL's odd behavior, which occurs when multiple timestamp columns are found in the same table. So let's jump over to the MySQL client and have a look. MySQL users often run into a bit of trouble when creating tables which contain both a created on and updated on timestamp column. The problem has to do with some rather, in my opinion, curious behavior on the part of MySQL. So if you take a look at this table creation statement, it looks pretty standard. We're creating a table named employees. It contains a column for storing the employee's name, and we have the aforementioned created on and updated on timestamp columns. However, if I go ahead and attempt to create this table, we will receive an error message. The error message has to do with the fact that MySQL only allows one timestamp column with current timestamp in the default or in the onUpdate clause. Well, looking back at the table creation statement, it doesn't seem apparent that this is in fact what we tried to do. The reason is that MySQL will automatically assign a default value of current underscore timestamp to any timestamp column which is identified as being not null and not having a default value, thereby conflicting with the secondary timestamp column definition, which has onUpdate current timestamp. So the solution to this problem is to use a slight variation of syntax for the created underscore on column. So I'll go ahead and start the table recreation process over. This time I will set a default value of 0 to the created on column and leave the updated on column as we did previously. And if you recall from the earlier slide, this will result in the updated on column not being set when the row is created, but being set every subsequent time that the row is updated. So with the columns in place, I'll go ahead and create the table. We can review table structure. Now notice I used default 0 for both of those timestamp values. That's just a shortcut really, because the default value actually looks like this. So, which is good because that more closely resembles what one would expect from a timestamp format. Now with the table created, if I go ahead and insert a new row, and I know I'm jumping ahead of myself here because we really haven't looked at row insertion syntax yet. However, I think it's important for you to view this behavior as it pertains to MySQL timestamps. So what I'm doing is creating a new row for the employees table. So we're saying insert into employees, specifically the columns name and created on, the values JSON and null. Now, MySQL, when we have not null set for a timestamp column, will ignore any attempt to set null to that column and instead will set the current timestamp. We already have a default value set for updated on and therefore do not need to name updated on in our column list here. So if I go ahead and create this row, review the table data, you'll see that created on has in fact been timestamped and updated on has not, which is exactly the behavior we want. However, we also want to make sure that when this row is updated, the created on column is not changed and the updated on column is. So I'll go ahead and update the name found in that row. Just changing the name from JSON to my initials. I'll update the row and return to the set of values. And as you'll see, the created on has in fact remained identical. The name has been changed as desired. And now the updated on timestamp has been updated. So it is possible to use multiple timestamp columns for this purpose within MySQL. You just need to be very careful of the syntax used at table creation time.